Hi, I'm Matt Clark, and I'm a professor at Sonoma State University. I'm in the Geography, Environment, and Planning department. And my expertise is in remote sensing, all different kinds of remote sensing, which is from drones to using satellite imagery to, in this case, using sound recorders to monitor biodiversity. We're here at the Fairfield-Osbourne Preserve, and we're going to show you a little bit of our recorders and our project. The Soundscapes to Landscapes project at a very high level is trying to monitor bird diversity across Sonoma County, so a county scale. We're trying to design a process that could ultimately be scaled to larger regions, multiple counties, maybe even across a state or even larger than that. The project is really, underneath it all, is run by a lot of citizen scientists or volunteers that come and help us place recorders out into areas around our county. And we get access to both public and private lands. In some cases, we actually mail recorders to landowners to put up on their property. Working with citizen scientists, particularly those that really know their bird calls and songs, we use their efforts to build a reference data set. And that's a very involved process. It's taken us over a year to do that. But then we take those data that we've collected on reference bird calls and songs, and we train a computer using machine learning technology that will go and automatically classify birds in our recordings. Up to this point, we've collected around 500,000 minutes of recordings at around 800 sites. So it's a lot of data. It's what we call a big data problem, and we really need to use machines and advanced technology to turn those sound data from the recorders into useful biodiversity data. Ultimately, what we do is we take the data from the sound recorders at different sites, and we can give you a list of species that occur at that site. And we connect those data of bird species with their location. We link that to remote sensing data, things that measure forest structure, for example, from LiDAR, phenology, the greening up and browning down of the vegetation from a multispectral satellite. We also get canopy chemistry, like the water content, lignin content of the canopy from hyperspectral sensors. And we bring all those spatial data, predictor data, together with the bird data. For each species, we map their distribution using these different kinds of spatial models. This is technology that's blending a lot of different things together: bioacoustics, remote sensing, machine learning, particularly deep learning technology, what people call artificial intelligence. We're blending all this together to create a new monitoring framework so we can track biodiversity over time. Some of the factors we're interested in tracking are climate change, how that may affect bird distributions, but also really short-term changes in the environment, such as from fire. So we're just getting our bird data from the sound recordings right now. So we haven't actually analyzed those in relationship to the remote sensing data that we're going to look at. However, we have published one paper so far where we looked at existing bird data that was already available for Sonoma County and linked it to various predictors in a spatial modeling framework. So that was kind of the prototype for what we're going to do with these new bioacoustic data. In that paper, we found that climate variables are really important for explaining the distribution of bird species in Sonoma County. And this is corroborates other findings from other studies that have looked at birds' distributions in other areas. One thing that was really unique about our paper is we brought in information on vegetation structure, so the actual physical arrangement of the branches and the leaves and trunks within, say, a forest. We brought that in using JEDI, the space-based LiDAR. And that was really unique for this kind of analysis. And we found that species that were related to conifer forests, needle-leaf forests with that we have around here, like redwoods, Douglas fir forests, as well as shrublands, were the kinds of species that were really well predicted with this structure data coming from the LiDAR sensor. So one of the key findings that we found so far in Soundscapes to Landscapes really has to do with the bioacoustic technology. We started off by placing smartphones in waterproof cases with a microphone attached, and they were kind of expensive and clunky to program and use. Recently, we transitioned to using audio Moths, these little low-cost recorders that are very cheap, and that makes it easy for us to buy a lot of them and hand them off to our citizen scientists and access more places in a field season. So it's been really revolutionary for us. We've actually done some tests and found these audio Moths have higher fidelity than our old smartphone approach. They're low cost, so there's a lot of new research being centered on using these new recorders. Another finding for us that we didn't know going into the project is that using this new modern artificial intelligence technology, deep learning, is really complicated. It takes a lot of data at the beginning where you know the bird's calls and songs as reference data. You need those data to both train the model and test its accuracy. And coming up with those kinds of data have been really challenging for us. It's a real limitation because these deep learning routines are data hungry. And we've been trying new ways to automate this process using citizen scientists that don't necessarily have any bird identification skills, but they can identify the birds by looking at their patterns visually when you represent sound in what we call a spectrogram, a visual representation. So we've been learning along the way how to build up our reference data set using citizen scientists, and then we're learning how to use deep learning. And we've been incredibly surprised and amazed by how accurate our models can be in detecting bird species. As you can see, we're really live in the field. It's starting to rain. So there was a question about whether research is a linear process, and it never has been for me. It's definitely nonlinear, and you often go down one path if you have ideas of how you think your research should progress and the methods you should use, and you learn along the way. And also, at least in my field, there's always technological developments happening while you're doing the research itself, and so you can pivot and adopt new methods. In our case, we pivoted and started using audio Moth recorders because we found they were much more low cost and actually better, and we can get a lot of them. So that's been huge for us. We also started with really rudimentary machine learning methods for doing bird classification in our sounds, and we moved into artificial intelligence, deep learning, because those methods were becoming more prevalent and accessible during the life of our project.
Hi, my name is Rose Snyder, and I am the project coordinator for Soundscapes to Landscapes. I work out of Point Blue Conservation Science. And I'm here to show you today how to set up an audio Moth. We use the low-cost and easily programmable audio Moth recorder. It's powered by 3 AA batteries that go into the back. And then there is a micro SD card on the side that stores the recordings. Has a simple on-off switch. We program the audio Moth to record 1 minute out of every 10, and it stays out in the field for about 3 to 4 days, so we end up collecting somewhere around 500 minutes of recordings at each site. We put it into this nice little plastic Ziploc bag, and then we strap it to some sort of vertical structure, usually a tree, sometimes a fence post. We leave it here for 3 or 4 days, come back and pick it up, and see what kind of excellent bird sounds we've collected.